Welcome! Today, we'll be tackling problem number 165, compare version numbers. This problem focuses on comparing two version strings and determining their order. It's a great exercise for practicing string manipulation and understanding comparison logic. Let's dive in. In this problem, we are tasked with comparing two version numbers, which are represented as strings. A version number is made up of one or more revisions, and these revisions are separated by dots. Each revision is a non-negative integer, and importantly, they do not have leading zeros. For example, version numbers like 1.0, 1.01, and 1.001 are all valid. When comparing these version numbers, there are three possible outcomes. If version 1 is greater than version 2, we return 1. If version 1 is less than version 2, we return -1, and if the two versions are equivalent, we return 0. Additionally, there are some key details to keep in mind. Revisions are considered equal if their numerical values match when you ignore any leading zeros. For instance, the versions 1.01 and 1.001 are both equivalent to 1.1. Another important point is that if one version number has fewer revisions than the other, we treat the missing revisions in the shorter version as zeros. For example, 1.0 is considered equivalent to 1.0.0. The output of this problem is an integer that represents the comparison result. Specifically, we return 1 if version 1 is greater than version 2, -1 if version 1 is less than version 2, and 0 if the two versions are equal. Let's look at the first example. Here, version 1 is 1.01 and version 2 is 1.001. The output for this example is 0, which means these two versions are considered equal. Now, why is that the case? To understand the output, we split both version 1 and version 2 into their individual revisions. For version 1, 1.01 becomes 1.1, since any leading zeros are ignored. Similarly, version 2, 1.001, also becomes 1.1. When we compare these revision lists, we see that they are identical, so the two versions are equal, and the result is 0. Now, let's consider the second example. Here, version 1 is 1.0 and version 2 is 1.0.0. Again, the output is 0, indicating that these two versions are equal. This is because when we split version 1, we get 1, 0, and when we split version 2, we get 1, 0, 0. The missing revision in version 1 is treated as a 0, so both versions are still equivalent. Let's move on to a third example. In the third example, version 1 is 0.1 and version 2 is 1.1. The output for this case is -1, meaning version 1 is less than version 2. Let's break it down. Splitting version 1 gives us the revision list 0, 1, while splitting version 2 gives us 1, 1. When we compare these revisions, we start with the first elements. Here, 0 is less than 1, so we can already determine that version 1 is less than version 2, and the result is -1. There's no need to compare further revisions once we've found a difference. Now, let's review the constraints and edge cases to ensure our solution works for all scenarios. To ensure correctness, we need to consider several constraints and edge cases. First, the length of version 1 and version 2 is guaranteed to be between 1 and 500. Both version numbers consist only of digits and dots, and no revision exceeds a value of 10,000. Additionally, the input is well-formed, meaning there are no leading or trailing dots, and dots do not appear consecutively. Some edge cases to watch out for include different lengths, where shorter versions like 1.0 should be treated as equal to 1.0.0.0 by appending zeros to the shorter version. Leading zeros also don't affect numerical equivalence, so 1.01 and 1.001 are equivalent to 1.1. Lastly, we must handle very large revision values like 9,999 without any risk of overflow. These considerations will help us design a robust solution to the problem. To begin, the brute force approach gives us a straightforward way to compare version numbers by treating them as lists of revisions. The idea is to split both version strings using the dot delimiter, which separates each revision level. Once split, we get lists of integers, where each element corresponds to a specific revision. The comparison then proceeds level by level. If one version string is shorter, we simply pad it with zeros to ensure both lists are of equal length. For example, if version 1 is 1.2 and version 2 is 1.2.0.3, we add zeros to the shorter list to make the comparison straightforward. We iterate through the revisions, comparing integers directly, and return -1, 1, or 0 as soon as we find a difference. While this approach is intuitive, it requires additional memory to store the lists and explicitly handle padding with zeros. The time complexity is linear in relation to the total length of the two strings, and the space complexity is proportional to the size of the split lists, which can be significant for long version strings. One drawback of the brute force solution is that splitting both strings upfront results in additional memory consumption. Furthermore, explicitly padding the shorter version with zeros adds a layer of complexity to the implementation. To address these issues, we can use an optimized approach that avoids the need for intermediate lists altogether. Instead, we process the strings directly using two pointers, which traverse the original version strings. With this method, we extract each revision number on the fly by parsing characters until we encounter a dot or reach the end of the string. These revisions are compared as integers, and if a difference is found, we return the result immediately. If no difference is found, we continue the process until both strings are fully traversed. Any trailing revisions in one version are implicitly treated as zeros during comparison, which aligns with the problem's requirements. This optimization significantly reduces memory usage while maintaining linear time complexity, as we only traverse each string once. The two-pointer approach has several advantages. First, it is far more memory efficient since we avoid creating intermediate lists for the revisions. Instead, all comparisons and traversals are conducted in a single pass, leading to improved performance. However, there are some challenges to consider. The implementation requires careful handling of string parsing and boundary conditions, such as ensuring proper behavior when one string runs out of revisions before the other. By carefully managing these details, we unlock a key insight: each revision is independent of the others, and trailing zeros in a version string do not affect its value. This means we can seamlessly treat missing revisions as zeros without explicitly adding them. Additionally, the ability to process revisions on the fly provides both time and space efficiency, making this approach particularly well-suited for long or complex version strings. These observations highlight why the two-pointer method strikes a great balance between simplicity and performance. The optimized two-pointer approach was chosen as the preferred solution because it offers the best balance between time and space efficiency. By processing the strings directly and avoiding intermediate data structures, we achieve a solution that is both fast and memory efficient. The iterative nature of this approach ensures we process each string in a single pass, and while the implementation is slightly more complex than the brute force method, the performance gains make it worthwhile. Comparing the two approaches, the brute force method is simpler to implement but incurs additional memory overhead due to the creation of intermediate lists and explicit handling of padding. In contrast, the two-pointer method scales better for large inputs, as it operates with constant space. Both methods handle edge cases, such as comparing 1.0 with 1, but the two-pointer approach does so without creating unnecessary padding. Ultimately, the two-pointer strategy is the most balanced and scalable solution, combining optimal performance with manageable complexity. Here, we aim to compare two version strings, version 1 and version 2, to determine if one is greater, or if they are equal. These version strings are formatted like XYZ, where each section, such as X, Y, or Z, represents a revision level. To solve this, the algorithm starts by parsing the input strings. First, we split each version string into a list of integers, with each integer representing a revision level. For example, splitting 1.0.1 gives us the list 1, 0, 1. Next, we ensure both lists have the same length, because if one version string has fewer revision levels, we treat the missing levels as 0. For instance, given 1, 0, 1, and 1, 0, we append a 0 to the second list, resulting in 1, 0, 0. This alignment step allows us to compare the versions level by level without worrying about unequal lengths. Finally, the algorithm compares the aligned lists to determine which version is greater, or if they are equal. To compare the aligned lists, we use a loop to iterate through their elements. For each index, we compare the corresponding integers from both lists. If the integer from version 1 is greater, we return 1, indicating that version 1 is greater. Conversely, if the integer from version 2 is greater, we return -1. If the integers are equal, we simply continue to the next index. The process stops as soon as we find a mismatch, which optimizes the algorithm by avoiding unnecessary comparisons. If all levels in the lists are equal, we return 0, indicating that the two versions are equivalent. Let's consider an example, comparing 1, 0, 1 and 1, 0, 0. At index 0, both values are 1, so we move on. At index 1, both values are 0, so we move on again. At index 2, we find 1 is greater than 0, so we determine that version 1 is greater and return 1. Key insights include the importance of padding shorter lists with zeros, which simplifies the comparison logic, and the ability to exit the loop early when a mismatch is found. We also account for edge cases, such as treating 1.0 as equal to 1.0.0, and handling empty strings by interpreting missing levels as zeros. To implement this algorithm, we rely on lists of integers to store revision levels. Lists are well suited for this task because they provide an ordered structure that mirrors the sequence of version strings, and integers can be directly compared using relational operators like greater than or less than. Regarding complexity, the time complexity of this algorithm is O, max, n, m, where n and m are the lengths of the two version strings. This accounts for splitting the strings into lists and iterating through their elements. The space complexity is O, n plus m, as we need to store the two lists of revision levels. Let's look at the code implementation. First, we parse the input strings by splitting them on the dot character and converting the resulting substrings into integers. Then, we align the lengths of the two lists by appending zeros to the shorter list. Finally, we iterate through the aligned lists and compare their elements. If a mismatch is found, we return 1 or -1 accordingly. If no mismatch is found, we return 0 to indicate equality. The final part of the code completes the comparison process. If all levels in the lists are equal after iterating through them, the function returns 0. Now, let's walk through an example. Consider the inputs version 1 equals 1.0.1 and version 2 equals 1.0. First, we parse these strings into the lists 1, 0, 1, and 1, 0, respectively. Next, we align the lengths by appending a 0 to the second list, resulting in 1, 0, 0. Then, we compare the list's element by element. At index 0, both values are 1, so they are equal. At index 1, both values are 0, so they are also equal. At index 2, we find that 1 is greater than 0, so we return 1 to indicate that version 1 is greater. This example illustrates how the algorithm handles alignment, comparison, and early termination efficiently. This Python implementation solves LeetCode problem number 165, compare version numbers. The task is to compare two version strings and return 1 if the first version is greater, -1 if the second version is greater, or 0 if they are equal. The compare version function begins by splitting both version strings using the split method. This turns the version numbers into lists of integers, where each integer corresponds to a revision level, e.g., 1.0.1 becomes 1, 0, 1. Next, the code determines the maximum length between the two version lists. This ensures that we can iterate through all parts of both versions, even if one version has fewer components. If one version is shorter, we treat the missing components as 0. The main comparison logic is implemented in a for loop that runs from 0 to max_length 1. During each iteration, the code retrieves the corresponding part from both version lists. If the current index exceeds the length of a version list, the code defaults to 0 for that version's part. The comparison is straightforward. If the current part of version 1 is greater than the corresponding part of version 2, the function immediately returns 1. Similarly, if the part from version 2 is greater, the function returns -1. If the two parts are equal, the loop continues to the next index. If the loop completes without finding any differences, the function concludes that the two versions are equal and returns 0. This implementation handles edge cases such as different lengths of version strings, trailing zeros, e.g., 1.0 versus 1, and empty components. It efficiently compares the versions in O, n, time, where n is the maximum number of components in the two version strings. The solution is concise, clear, and adheres to best practices for solving this problem. This is the Java implementation of LeetCode problem number 165, compare version numbers. The logic mirrors the Python solution, where both version strings are split into parts using the dot delimiter. The algorithm iterates through the parts of both version strings, comparing corresponding segments as integers. Any missing segments in the shorter version are treated as 0. The implementation uses Java-specific features like string.split and integer.parseInt, ensuring correctness and simplicity. The method returns 1, -1, or 0 based on whether version 1 is greater, lesser, or equal to version 2 respectively. We start by breaking down the first example where version 1 is 1.01 and version 2 is 1.001. First, the input strings are split by the dot character, resulting in 101 for version 1 and 1001 for version 2. Each of these parts is then converted to integers, giving us v1 underscore parts as 1, 1, and v2 underscore parts as 1, 1. Next, we determine the maximum length of the two versions, which in this case is 2, since both have 2 parts. Now, we enter the comparison loop. In the first iteration, we compare the first elements, one from v1 underscore parts and one from v2 underscore parts. Since they are equal, we continue. In the second iteration, we compare the second elements, which are also both 1. Again, since they are equal, we complete the loop without finding any differences. At this point, since all parts of the two versions are equal, the function concludes by returning 0. This indicates that version 1 and version 2 are equivalent. To summarize the intermediate states, v1 underscore parts and v2 underscore parts are both 1, 1, and during the loop, the values compared were v1 equals 1 and v2 equals 1 in both iterations. The final output is 0. Shifting our focus to the second example, version 1 is 1.0 and version 2 is 1.0.0. After parsing, splitting the strings results in 1, 0 for version 1 and 1, 0, 0 for version 2. Converting these to integers gives v1 underscore parts as 1, 0 and v2 underscore parts as 1, 0, 0. The maximum length is determined to be 3, because version 2 has 3 components while version 1 has only 2. We now proceed to the comparison loop for this example. In the first iteration, v1 is 1 and v2 is also 1. Since they are equal, we move to the next iteration. In the second iteration, v1 is 0 and v2 is also 0. Again, they are equal, so we continue. In the third iteration, we notice that version 1 has no third part, so we default v1 to 0. Meanwhile, v2 is the third component of version 2, which is also 0. Since v1 and v2 are equal here as well, we finish the loop without finding any differences. Since all parts are equal across the two versions, the function concludes by returning 0, indicating that the two versions are equivalent. To summarize the intermediate states for this example, v1 underscore parts is 1, 0, and v2 underscore parts is 1, 0, 0. During the loop, the values compared were v1 equals 1 and v2 equals 1 in the first iteration, v1 equals 0 and v2 equals 0 in the second, and finally v1 equals 0 and v2 equals 0 in the third iteration. Since no differences were found, the final output is 0. Now, for the third example, version 1 is 1.0.1 and version 2 is 1.0. Splitting the strings gives us 1, 0, 1 for version 1 and 1, 0 for version 2. After converting these to integers, we have v1 underscore parts as 1, 0, 1, and v2 underscore parts as 1, 0. The maximum length of the two versions is determined to be 3, since version 1 has 3 components while version 2 has only 2. In the comparison loop for this example, we begin with the first iteration where v1 is 1 and v2 is also 1. Since they are equal, we move to the next iteration. In the second iteration, v1 is 0 and v2 is also 0. Again, they are equal, so we proceed to the third iteration. Here, v1 is the third component of version 1, which is 1, while v2 defaults to 0 because version 2 has no third component. Since v1 is greater than v2, we immediately conclude that version 1 is greater, and the function returns 1. To summarize the intermediate states for the third example, v1 underscore parts is 1, 0, 1, and v2 underscore parts is 1, 0. During the loop, the values compared were v1 equals 1 and v2 equals 1 in the first iteration, v1 equals 0 and v2 equals 0 in the second, and finally v1 equals 1 and v2 equals 0 in the third. Since the comparison in the third iteration revealed that version 1 is greater, the final output is 1. The time complexity of the solution can be analyzed in 3 main steps. First, splitting the version strings by the dot delimiter takes time proportional to the total length of both strings. Specifically, if version 1 has a length of n1 and version 2 has a length of n2, this step requires n1 plus n2 time. Next, mapping the split parts into integers also takes n1 plus n2 time, as the total length of all the substrings from both versions is proportional to the input lengths. Finally, we compare the parts of the two versions in a loop that iterates up to the maximum number of parts between the two arrays, which is max, k1, k2. Since each iteration involves a constant amount of work, this step takes max, k1, k2. Combining these, the overall time complexity is dominated by the splitting and mapping steps, leading to a final time complexity of n1 plus n2. The space complexity of the solution is primarily determined by the storage required for the split parts of each version string. Splitting version 1 and version 2 into arrays of integers requires space proportional to the number of parts in each version, which is k1 plus k2. Here, k1 is the number of parts in version 1, and k2 is the number of parts in version 2. Beyond this, the solution uses a small number of temporary variables, such as those needed to hold individual parts during comparisons, which take constant space, 1. As a result, the total space complexity is dominated by the storage for the split parts, resulting in k1 plus k2. When comparing this approach to a brute force or naive method, we can see significant improvements. A naive solution might involve padding the shorter version string with zeros and directly comparing the entire strings. This would require creating new strings of length max, n1 and n2, which inflates both the time and space complexities to max, n1, n2. In contrast, the provided solution avoids these inefficiencies by directly comparing integer parts. Analyzing the best, average, and worst cases, the best case occurs when the versions differ early, such as in the first part, allowing the loop to terminate quickly. While the time complexity remains k1 plus k2, the actual runtime is much faster due to early termination. In the average case, the versions differ after comparing a few parts, maintaining the same time complexity. In the worst case, every part of both versions must be compared, but even then, the total time complexity is still n1 plus n2. Mathematically, the solution processes the input with linear operations, ensuring that both time and space complexities are linear, specifically n1 plus n2 for time and k1 plus k2 for space. When comparing version numbers, there are a few common mistakes to watch out for. First, not normalizing versions with trailing zeros can lead to errors. For example, 1.0.0 and 1 should be considered equivalent because trailing zeros are insignificant, but if this isn't accounted for, it can result in incorrect comparisons. Next, failing to handle empty or unequal length arrays properly can also cause issues. For instance, comparing 1.2 with 1.2.0.0 requires padding the shorter version with zeros to align the components, otherwise, the comparison becomes misaligned and produces the wrong result. Another mistake is using string comparison instead of numeric comparison for version components. This is problematic because strings are compared lexicographically, so 10 would incorrectly appear smaller than 2. To ensure correct results, always compare these components as numbers rather than strings. Now, overcomplicating the logic is another frequent issue. Solutions that involve nested loops or unnecessary intermediate data structures can increase both time and space complexity, making the code less efficient and harder to understand. Additionally, not accounting for edge cases can lead to unexpected bugs. Examples include comparing 0.0.0 with 0 or handling versions with only one component, like 3 versus 3.0.1. These special cases must be explicitly addressed to ensure consistent behavior. In interviews, it's important to break the problem into clear steps, such as splitting the strings, normalizing their lengths, and comparing each component. Be sure to communicate your thought process and ask clarifying questions, like whether trailing zeros are significant or if the inputs are guaranteed to be valid. This problem tests your attention to detail and your ability to handle edge cases while designing a clean and efficient comparison. Focus on readability over cleverness, as a straightforward solution with clear comments is more valuable than a convoluted one. If you have extra time, you can discuss trade-offs between iterative and recursive approaches or mention space-saving strategies for handling large inputs. This problem is closely related to others that involve string manipulation and comparisons. For example, 68. Text justification, 43. Multiply strings, and 415. Add strings all require breaking down strings into components and processing them systematically, much like 165. Compare version numbers. When considering alternative approaches, the two-pointer technique is a useful option. It provides more manual control over iteration and avoids creating intermediate arrays, though it can result in slightly more verbose code. A recursive solution, on the other hand, is elegant and may be appealing in an interview setting where recursion is emphasized. However, it's generally less efficient due to the overhead of function calls, making it less practical for production scenarios. Finally, leveraging built-in functions like Python's zip_longest can help handle uneven lengths directly, resulting in cleaner, more concise code. The trade-off here is that it depends on familiarity with specific libraries or functions, which may not always be ideal in all contexts. To understand the complexity of this problem, let's break it down. The time complexity is O, max, n, m, where n and m are the lengths of the two version strings. This accounts for the time required to split the strings and compare their components. On the space complexity side, it's O, n plus m, as the split components need to be stored temporarily. However, this can be reduced with in-place parsing techniques that avoid creating additional arrays. Keeping these complexities in mind can help you optimize your solution and explain its efficiency during an interview. Great job! We've successfully broken down problem number 165, compare version numbers. Remember the importance of string parsing and segment comparison for problems like this. Thanks for tuning in, and feel free to explore more problems to sharpen your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!